Mahavir sir?
I can hear you. Yes. Good morning.
Mahavir sir, am I audible?
Yes, you're audible. Can you hear me?
Yeah, sir, sure.
Yeah.
Welcome to the session, sir. Participants, Mahavir Jhawar sir is working as an assistant professor at the Department of Computer Science and Engineering, Ashoka University. Sir has received his PhD degree in computer science from the Indian Statistical Institute, Kolkata. He was Department of Computer Science and Engineering, University of Calgary, Canada. His research areas are cryptography with particular emphasis on public key cryptography, lattice-based cryptography, blockchain, protocols in applied cryptography, and network and system security. So, from the Department of Information Science and Engineering, I wholeheartedly welcome you, sir, for the session. Thank you for delivering the talk. Thank you, sir. Over to you, sir.
Yeah, thank you. Thank you very much for the kind words.
Yes.
Let me share the screen.
Yeah, sure, sir.
I hope the screen is visible.
Yes, sir.
Yeah. Okay, thank you. So let's get started. I'm really hoping that we don't experience any power cut from my end. That's one thing. If there is any power cut, I usually take a minute to be back because of the power backup. So please excuse me if we experience any power backup problem. Okay. So I'm not sure what I mean as a background. What can I assume? Okay. But I'll try to keep the talk simple enough. So if some of you already are coming in with a good background in, for example, Bitcoins, then please excuse me. Otherwise, I think if you are new to this field, I'm sure you will take away a few good things. Okay. I have chosen basically one of the issue that blockchain in large faces, and of course its applications also, and in particular the cryptocurrencies. Okay, and so that's basically about that I'm going to discuss the one particular scalability issue. Okay, and then we talk about a way to address the scalability issue. So as the talk abstract says, despite the growing adoption of blockchain-based currencies, making fast payments at scale remain a challenge. That's and payment channels, one of the prominent tools to improve the scalability of blockchain-based currencies. They allow two users to rapidly exchange money with each other without sending transaction to the blockchain, and that's because we know that by its design, you have to send every transaction to the blockchain. Okay, and that is problemsome. Okay, because blockchain, if it is permissionless, as you know, it would take a lot of time to approve those transactions, and that basically puts a limit to the number of transactions that you can process in a certain period. Okay, so payment channel basically overcome this limit by not sending all the transaction to the blockchain. Okay, so that's basically, we will talk about more on this issue specifically to the Bitcoin. Okay, so for the talk we will keep our focus on Bitcoin. We will keep make the issue clear for Bitcoin, and then we talk about payment channels, and of course one particular protocol which is very state of art protocol that I'll talk about, and hopefully if I have time, then I will go ahead and I'll introduce the anonymity issues in cryptocurrencies, and in particular Bitcoin, and then I'll talk about ways to address them, and then put together and talk about basically something called payment channel hub, which addresses both payment channel and the anonymity issues together. Okay, so let's get started. Uh, I think every talk has to start with a brief introduction to the blockchain in general. So I'll briefly introduce. I mean, over the last couple of days, you must have gone through quite a bit details on Bitcoin blockchain. So, but I'll just add quickly my perspective, and so that it's useful for the talk. Okay, so before we get into, we know that blockchain is also called distributed ledger system. Uh, so let me introduce what is a centralized ledger system, and then we move from there to the distributed ledger system, which is also called blockchain. Okay, and a centralized ledger system is I mean, basically it's used used for, I mean, you can think of any database management when it is done centralized. Uh, Particular examples is basically bank or insurance company. Okay, and here's a quick glimpse into such a system. Okay, so as I said, by a ledger, you can think of as a database. Okay, which has key value pairs, a database having key value pairs. Okay, as you can see, and there are this database is managed at one single server. Okay, which is very centralized, and then there are clients who basically want to update these key value pairs. Okay, and in order to do that, they basically make transactions. But because this is centralized, all transaction will end up going to the database server, this one, and this database server will basically order this transaction, and then of course it will also validate this transaction order, maybe in terms of the timestamp, and each transaction will get validated. And the validation, as we know, it's in terms of some rule book. Okay, so if a transaction is proposing to change value of a certain key, then of course it has to be validated that it is coming from, I mean, as per certain rule. Okay, and but all of these rules are with the centralized server, so it receives all this transaction, it orders them, it validates them following some rule, and then it applies the effect. For example, as you can see here, there are 4 transactions, and after the ordering and the validation, the centralized server found that, like, this is the current state, for example, but after this they found that transaction 1, transaction 3, 4, and 7, this is the order of the transaction, and all of them happens to be valid. And then they basically apply their effect on the database, and as a result of that, as you can see, the value 2 gets updated at the key 2. Similarly, value 3 gets updated at key 3, and so on. And that's now updated database. Okay, and that's how the system moves forward. Okay, as more and more transactions are received by the centralized database system server, and they continue to update this. Okay, so ledger is basically, you can imagine, is uh, basically the collection of all the transactions that are ever made in the system. Okay, and the database, the current state of the database is basically can be arrived at by uh, by basically you can derive them from looking at all the transactions that ever made in the system. Okay, so this is so the latest state of the database is also called the world view of the ledger, and sometimes we call ledger as the world view plus all the transaction records, and sometimes we also call ledger as just the record of all transactions. So there are various ways of referring to it, but as we know, the interesting part is that the collections of all transactions ever made in the system, that's primarily is the base, and the worldview at any point can be derived from the transaction that were made up to that point. Okay, but the problem here is very simple, because everything is centralized, and the ordering and validation is done by a central server. Okay, and as I said, in the bank, in the application of banking, these key value pairs are basically the keys are basically account numbers of account holders, and the value is basically their balances. Okay, and transactions are basically when account holders making transaction, that is receiving some money to their account or sending some money out of their account. So these are basically transactions. Okay, and this is very simple. You can see, like if I send a transaction, for example transaction 3, requesting that certain money should be deducted from my account and should be given to somebody else, and if this transaction is valid in the sense that I am able to authorize myself properly to the central server, the bank server, then what happens? Basically it's get affected and my balance gets deducted and somebody else balance is basically added up with that amount. Okay, and that's how the system moves. The decentralization of the ledger is when you don't have one central server who basically receives all the transactions. You can think of like this, where you have the same database but replicated across many servers. Okay, and now transactions are, they may be physically far apart. Okay, maybe working in different time zones and so on. Some of them may be down and some of them may be corrupt and so on. You must have heard all of this, but the point here is that that not all of them, I mean there's no one central server, there are multiple servers and all of them managing the same database. So the problem here is that they should have the one view of the database. Now imagine at one point they have can you hear me? There was a power cut. Am I audible?
Yes, sir, you are audible, sir.
The screen is visible, yeah?
Yes, yes.
Yes, okay, good. So you see, now the point here is that you have a centralized server not there, and you have the basically all these servers, and they have at some point imagine the same view of the database, and now the servers basically received transactions from different clients. And as you can see, this server is receiving a transaction here, this server is receiving a transaction here, and so on. Okay, and now the idea is that and through replication they might agree on the, you know, the all the transaction that were received by the system as a whole. Okay, but the question is that now you have to basically order this transaction, validate this transaction, and so on. Now the ordering maybe in terms of timestamp is not so easy now, primarily because these transactions I mean they were received at different timestamp, and more importantly some server may not follow, you know, the ordering correctly and so on. So there's a huge problem there. So then we know that there has to be a consensus mechanism by which they should agree on a order. And as you said, as you must have heard through the talks, that there are various ways you can arrive at these ordering of these transactions. and then of course you validate this transaction as per the rule, and this is basically your consensus mechanism. Okay, and as you see here, that after this happens, you basically the entire network basically agree on the following order, and once they agree on this, as per that order, everyone has to apply the effect on their database. As you can see, uh, they agree on this order, and once when they agree on this, they have to basically go ahead and apply the effect on the database as per the transaction in this order. Okay, so that's and of course a lot of things goes into this distributed consensus mechanism. Okay, where we will not definitely going into that, because this talk is definitely looking at the a layer above. Okay, not precisely in the blockchain. Okay, and as part of the distributed consensus mechanism, you have seen that that you see all these transactions, once they were agreed upon, you have to link them properly, so that nobody should be able to retrospectively make any changes to the previous agreed upon transaction and so on. Okay, and that's how basically we have this concept of blockchains, where you have blocks of transactions that you have agreed upon previously, and then of course once you have newer blocks of transaction that are being approved by the network, they have to be linked together in a way such that retrospectively you provide a fault tolerant kind of a mechanism. Okay, so that's about the entire brief basically overview of the blockchain technology, how it works. And as you can see, here is only one rule book. So basically every transaction is put to test by against one rule book only. Okay, but then we also know that there could be many rules, okay, in the blockchain. So when I make a transaction, I might say that you validate my transaction against a particular rule. So therefore it requires also that the rule books also have integrity that is basically provided by the system. And as you know that for example, Ethereum is for blockchain Bitcoins, you have basically one kind of a rule and slight variant of that. But in the Ethereum's transaction can be validated against multiple rules, okay, which are basically called smart contracts. Okay, so it's the same mechanism, and of course the clients here also propose as part of their transaction new rule books, and once they are agreed, they are also find their place in the ledger forever. And so that in the future, when you make a transaction, you might say that, okay, my transaction has to be validated against a certain rule. Okay, so the participant in the network will ensure that they will find that rule and basically validate your transaction against that rule. Okay, so as you can see, this is one picture where there are several rules, and for example, this transaction, when it's proposed, it says that, okay, my transaction has to be validated against something called rule Z, and that rule Z may be already there previously, okay, proposed as part of a transaction. Okay, so that's like more general picture. But in this talk, we are concentrating on Bitcoins. So for Bitcoins, let's look into all how the key value pairs looks like, and of course how this rule basically looks like. Okay, which we call Bitcoin scripts or Bitcoin smart contracts. Okay, so key value pair is in Bitcoin is basically the following. Key is basically a Bitcoin address. Okay, it's okay, and the value is basically a certain amount of Bitcoin that are present at the Bitcoin address. And if you want to make any changes to that Bitcoin, so basically if you want to consume it, if you want to spend it, then there are conditions which are specified in the rule book, okay, which is also present at part of the value. Okay, and you have to basically you know uh, come true to those conditions in order to basically spend some Bitcoins which are available at that Bitcoin address. So basically so in a general term, if you want to change the value at a certain key in the Bitcoin, you have to make a transaction accordingly. Okay, and that transaction will should have a certain solution to the condition that were already specified here, and basically if you can satisfy them, you will be able to spend these coins. So that's the whole idea. Okay, so as I said, a Bitcoin transaction allows a Bitcoin user to propose changes to several key value pair, and the way the Bitcoin system work, you can basically make changes to this key values pair through one transaction at a time. Several of them you can do. Okay, and as I said, the transaction should carry necessary information along for its successful validation. Okay, so as we move forward, we are going to look at the couple of scripts here okay, and then we'll get to know that what are those conditions, and definitely and then accordingly we'll also describe transactions. Okay, uh, which successful transaction basically. Okay, so I'm assuming because for this to know, we have to know how the Bitcoin address are computed, and basically because they in order they will require in order to understand the rule book. Okay, so I am not going through the underlying signature schemes. I am sure somebody must have covered it as part of the talks. Okay, so but just for completeness, as we know that if you become a user of a Bitcoin, okay, so you will create a Bitcoin address, and at that address you can receive money and so on. Okay, so that address is of course is computed out of a public key, public key, which is a public key for a digital signature. And when you want to spend that money, then you have to use this corresponding secret key, and basically you have to sign something. Okay, and the underlying signature scheme for Bitcoin is ECDSA, and these are specific parameters for that signature. I am not going into these details. I'm sure somebody must have picked it up, but as a matter of fact, I just want to just quickly mention that when you become a user of the Bitcoin, you basically create a pair of ECDSA public key and secret key, and your public key is basically looks like following. You see, public key is basically a group element. Okay, elliptic curve group element, and if you want to think it more carefully, you can think of them as a pair of elements. Okay, uh, and they were of certain size. Okay, so basically 512 bits of entire string, which can be looked at as a pair of two elements, and they represent element in the group. Okay, but the point here is that you create a public key, and there is a corresponding secret key that you also create, and that's how you basically begin the process of opening a Bitcoin address. Okay, so now let's see how do you receive Bitcoins. Okay, so it's pretty much like opening a bank account, and that's how you create a account, and then of course you give your account number to somebody else to basically give the money. Okay, in the Bitcoin it's the similar. Okay, as I said, in the bank account you create your account number, and while creating you also choose a secret pins, and then account number is used to receive money. And then if you want to spend your money, you have to basically use your secret pin to establish ownership of the money so that you can spend it. That's what works in the bank account. But for Bitcoin account, it's pretty much same. As I said, if you want to be a user of the Bitcoin, you have to basically, as I said, very informally, you have to open a Bitcoin account, which is same as you basically create a ECDSA key pair, a public key and a secret key. Okay, so users in Bitcoin, they create a public key and secret key, and then there is a bit of an encoding happens on the public key. I'll talk about that encoding because it needed to be discussed a bit. But the point here is that after this encoding of your public key and your secret key as a pair basically represents your account number and secret pin, analogous to bank. Okay, so they work like the bank, and as if like this is your account number and this is your secret pin. Okay, and the encoded PK is basically is the Bitcoin address, as I said, and we use our Bitcoin address to receive Bitcoins. So basically Bitcoin address is, as I said, it's like account number, so we use it to receive Bitcoins. And if you want to spend Bitcoins, then we have to use our secret key, and which is same as like the secret pin, and which is used to establish ownership of the money. Okay, and okay, and that's what we going to quickly see. Okay, okay, so there are several, depending on different encodings, we can have different types of Bitcoins addresses, but I will just go ahead quickly and show you the most popular Bitcoin addresses, which are called P2PKH address type. Okay, and as I said, I'm going to quickly give you that the encoding, when you have the public key, how do you basically create a Bitcoin address which is of P2PKH type. The step one is that you have the public key, you basically apply SHA-256. So SHA-256, as you know, is the hash function whose output is basically 256 bits. So you apply SHA-256 on the public key and you get your H1, which is a 256 bit number. And on H1, you apply RIPE-MD160. So RIPE-MD160 is another hash function, as you know, and we apply that hash function on H1 and we get H2. So these are the first two steps. Okay, and then we do the following: we apply, we append the H2, basically prepend, not append, prepend H2 with a byte which is all 0. So it's hex notation for 1 byte, basically 0, all 0, and that's my H3. And then I again compute, SHA-256 twice on H3, which is H4 now, and then I basically compute H5, and H5 is basically my H3, as you can see here, as it is, and then I take the first 4 bytes of the H4 and that I append it to H3. Okay, and finally H5 looks like as follows. As you can see, H3 and the first 4 bytes of H4, and H3 is basically this entity, the all single byte having all zeros, and then H2. So basically we put, okay, so A is basically all 0. Okay, A is all 0, H2 as it is here, and the first 4 bytes of H4, and that's my H5. Okay, and then there is this base 58 encoding. Like you see, you have different encoding streams. You have seen like UTF, ASCII. Similarly, base 58 encoding is popular for Bitcoin, and it's not difficult. I'm sure you have seen it, but otherwise you can just go through this very easily. And that's basically, you see it, it basically turns the bytes into alphanumeric result. Okay, so you apply base 58 encoding on H5, and then that becomes your Bitcoin address. Okay, so the addresses, Bitcoin addresses that you see, if you go to any blockchain explorer and if you look at the Bitcoin addresses, you will see that the address, most of the addresses are P2PKH type, and then you can imagine that those addresses are basically computed like this. So again, once again, you have the public key. When you become a Bitcoin user, you generate a public key secret key pair, and then you apply this encoding on your public key, which basically your mobile client will do it for you. And the steps are follows: you first apply SHA-256, then RIPE-MD160 on public key, and then you arrive at H2, and you prepend this with single byte 0, and then you apply SHA-2 double on H3, and then take the first 4 bytes of H4, and basically you construct H5 the following way, and then you apply base 58 encoding on H5, and that's how you get the P2PKH address. Okay, and one thing here, it's interesting that if you receive the base 58 encoding of H5, which is the P2PKH address of any user, from there from this P2P cache address, you will not be able to get its public key, okay, but you will be able to compute H2, which is basically RIPE MD 160 of RIPE SAR 256 of public key. That's easy, because if somebody gives you its P2P cache address, you know that the P2P cache address is processed like this, so you can easily do a inverse of the base 58 encoding, and then you will arrive here, and from here you basically take out the first byte and the last 4 bytes, and that leaves you with H2, and H2 is basically this quantity, okay. And you cannot do further reversion, because that's basically amounts to finding pre-image of hash function, which is difficult, okay, but you can do this. That's important. Okay, here is a notation. We also call this as hash 160 of pk. So this notation, when I write hash 160 of pk, by that I basically means on pk we have applied 2 hash functions in this order, first SHA 256 and then RIPE-MD 160. Okay, so that's about Bitcoin address. So therefore we have seen that if you become a Bitcoin user, you basically create a key pair, and then on your public key you basically make this computation, and you basically compute a Bitcoin address, which is P2P cache type, and then you give this address to somebody and basically request that they send money to at this address. Okay, so that's our next part, receiving Bitcoins. Okay, and I will just immediately go ahead and give you the transaction, and then basically we decode that how transaction the structure a little more detail. Okay, so assume you have a user A, and he has just become a Bitcoin user, so that basically means he has created a key pair, a ECDSA key pair, so which has a public key and a secret key. Okay, and B be another Bitcoin user who wish to transfer Bitcoins to A. So therefore, B must acquire the Bitcoin address from P A, which is basically means it will acquire P2P cache address computed using the public key of A. and then we will see that we will actually give you 2 transactions here. The first one basically where B will send money to A, and the second one is when A will actually subsequently spend that money. So you see, if the first transaction will give you where B will send money to A, okay, and as a result, if that transaction is approved, then in the world view, basically there will be key value pair created where the key value pair will be the following. The key will be the basically Bitcoin address of A, and the value is basically the money which it receives from B, okay, along with some rule book that specifies how A can subsequently spend that money. And then we will also say a second transaction where A will basically in future spend that money. So therefore you will see that A will also make a transaction, and as I said, the A's transaction should have solution to what is specified in the rule book for that key value pair. Okay, so we'll put those together here very quickly, and that hopefully will give you an idea about how transactions are basically made to spend money and receive money. So as I said, the first is T offer. Okay, so there are a few things. Every Bitcoin transaction has an input and output, as you can see here. There are many fields. We will come to that, but I'll shortly give you the following. So let's look at the T offer transaction. So T offer transaction here is basically referring to the transaction. Look at this row only. So T offer is the transaction that B is actually making to send money to A. Okay, and don't worry about its input, but what is important is the output. And basically the output is the following. The transaction says, okay, you send basically X Bitcoins, okay, and then you put as part of the output a rule book, okay, and the rule book is as you said, it's there are a couple of commands and there is a bit of data here. What are the commands? The commands are as follows. There is this op duplicate, op hash 160c. Op is basically operation duplicate, as we call it, operation hash 160. And then there is this data. And what is the data? Data is basically hash 160 of pka. How is B will get this? As I said, when A gives its P2 pkh address to B, in the previous slide I showed, B will reverse from the P2 pkh and arrive at this quantity, which is basically ripe MD and SHA-256 of pka, which is hash 160 of pka. Okay, so that's like 160 bits that it computes from this address, and it put it here. And then it followed, and then follows another two commands, op equal verify and op check signature verify. Okay, so you see, when B simply make this transaction, you can think of them, it's like a checkbook. Okay, you can think of them, it's like a checkbook where B is writing a check for A, and B says this is the amount, basically, I'm spending, and basically, and it also write a rule book. In the checkbook we write exactly the account number, but here we actually write a rule book. And the rule book, we will see that the way it is written, we will see that this basically says that only A can basically spend this money in the future. Okay, and that's about the first transaction. Now the second transaction is in the future when A spend this money. Okay, and that's like T fulfill. Okay, and when it's like the user A now is ready to go to the, basically spend this money. It knows that this money is available here, and once this T offer is basically accepted by the blockchain, as I said, key value pair will be created, and the value at that key value pair is this. The value is basically this X bitcoins and this rule book, and together we call this as UTXO, or unspent transaction output. Okay, along with this rule book. Okay, and A in future when it wants to spend this, A basically have to now make another transaction, that's we call it T fulfill, and in that transaction basically A will be saying that, okay, here is the key value pair where I want to change the value, and the change the value basically means I want to spend this money. And so of course T fulfill will have to refer to the transaction, and as part of which this was created, and that's basically is referred by transaction ID. Okay, and as I said, this is the these are the two subfields of the input field in this transaction, and hash of the T offer is basically the transaction ID. So with this you will be able to arrive at this transaction, and then as part of the T fulfill, you will also have to give solution to the condition which are set in this rule book. And we see that as part of the solution, we are actually providing some signature and the public key of the A, and we will see that why this will basically work. Okay, why this will work. Okay, so let's see. So when T offer was made, B is basically transferring the transaction, some money, and creating the key value pair, and the money is there, and basically it says that this rule book has conditions, and whoever can satisfy those conditions will be able to spend this money. And the condition precisely here means that this money is basically locked to a user whose public key is pka, and whose hash of that public key is basically given here. And if that user want to spend this money, that user should provide its public key first, and it should also provide a signature using the corresponding secret key. So which is same as, like, again, when we make a transaction in the bank using a check, we sign our transaction we sign on the check. So it's basically the same here. And as you see here, when A is want to spend this money, the input to the transaction is basically the reference to this transaction, and then basically the details here where you actually have the public key of A included, and then there is a signature which is A is doing using its secret key, and the signature is done on a message. Okay, and that message is basically the transaction itself. Okay, and as you can see, if you think of this transaction as a checkbook, you are basically signing on the checkbook, which is same here as basically signing the transaction using the secret key. Okay, so this rule book in Bitcoins are also called script pub key, and the solutions in the later transaction when you want to spend this is also called script sig. We also call them lock script, and we also call them unlock script basically. So in a way, T offer is basically locking some Bitcoins with this lock script, and whoever wants to unlock this or spend this, they should provide an unlock script. Okay, that's the whole idea. And let's see how this transaction validation happens. Okay, so this is the transaction. This is the first transaction from B to A, and the second is from A to B. Okay, so and broadly speaking, the transaction is like this: OP duplicate OP hash, and I have just replaced this hash 160 pk by public key hash. Okay, and corresponding unlock script or script sig is basically you have to provide the signature and the public key, whose public key hash is here. And as I said, script pub key is also called lock script for this UTXO, and script is called basically unlock script for this UTXO. And let's see how this happens, how this execution happens. And we know that this validation, when T offer is made and approved by the network, and later when T fulfill is proposed by A, this transaction of course has to be validated by the Bitcoin network, and we just want to see how it is done. Okay, without actually going into the details of what miner does, we just look into the details what the validation of the transaction is done. Okay, and that's done the following way. As you know that basically this is the execution is done in a controlled environment, and that controlled environment is basically a stack based execution. Okay, so let's see, we quickly go through that. So when this transaction basically when this T fulfill T fulfill when goes out into the network, let's see how this is gets executed. Okay, so miners will basically receive those T fulfill transaction, and T fulfill will have basically the unlock script, but because of the T fulfills transaction ID, from here they will be able to come here, and they will know that T fulfill basically want to spend this money. So there is this lock script also they will find out, and they know that this unlock script should be unlocks basically this lock script. Okay, so they will basically put unlock script and lock script side by side, and as you can see, unlock script is basically signature and public key, and lock script is basically this long lock script. Okay, and how the execution happens, let's see. Execution happens from left to right, and as I said, the arrow points to the argument to be executed next. Okay, so right now we start with the empty stack, and you have this entire script you can think of as like a program, and there are some data in the program and some commands, and we have to sequentially execute them from left to right. Okay, in a stack environment. Okay, so you have the signature. We are basically going to when data is there, you put the data on the stack. Okay, then you see next you move, and you see now you have again data, you again move it here. Okay, okay, and next is basically the command, which is OP duplicate. When you arrive at this command, basically this means whatever is the top element on this stack, you basically make a duplicate of it. So that's what we do. We move next, and then there is this command OP hash 160, and that basically says what? That whatever is on the top right now, you compute hash 160 of that data. So hash 160 is what basically we apply SHA-256 first, and on the result we apply RIPE-MD 160, and that's what we are going to do right now. Public key is on the top. We apply this hash 160 function and replace the public key by this result. And as you see, we apply on this public key SHA-256 and then RIPE-MD 160, and whatever is the result, we basically put this on top of it, and that basically, and we move to the next. And then again there is a data here. Okay, so we are going to dump the data on the stack public key hash. And now we see the next command is op equal. Op equal says you look at the first two elements in the stack and just check them for their equality. If they're equal, then basically you remove all of them, both of them, and if they're not equal, you basically means that there is an error and you stop basically working. Okay, and at this point basically this and this equal means basically, because this was actually in the rule book, B says that this is the public key hash of the user A, who can only basically spend the money. So therefore, if A is trying spend the money, A should provide its public key. Yeah, and if it is correct, then both of them are equal actually, and in this case it is so, and therefore this is removed. And now we reach OP checksig, and OP checks is that we expect that now the top two elements in the stack are basically public key and a signature, and you should run the digital signature verification algorithm, and if the verification says correct, then basically you see it is correct, otherwise you basically again abort and saying the transaction is wrong. And in this case, as you can see, for this to correct, this signature, because this public key is the public key of A, and this signature should be the signature that the user A must have basically generated. Okay, and if it is correct, then it will be output 1, and therefore you will remove it, and you basically executed the entire script put together, and at the end the stack is empty, there's no error, and so therefore basically this means basically transaction was valid. Okay, so that's how the transaction gets executed, and this is only one type of transaction, which is called P2PKH transaction type. Okay, and so that's how, and if it is done, then basically the transaction is validated, and then on top of it there is of course Bitcoin's own distributed consensus is there, by which it has to go into some block and so on. Okay, but finally if it is approved, then of course the A will be able to spend that money and can transfer this money to somebody else. That's the whole idea. So now at this point, I think we can now go slightly deeper into the transaction structure. Okay, so we already show that the transaction has an input and output, and the point here is that I said the transaction can actually have multiple inputs and multiple outputs. So basically, for example, A has several Bitcoin addresses, and A has some Bitcoins available in all of these addresses. A can basically spend all of them together and again send to multiple outputs. Okay, so that is what the transaction allows, and in general, as I see, the transaction structure is this, that you have multiple transaction inputs and multiple transaction outputs. And as we saw, every transaction input, if you look at any input here, that is like this. You have to have a transaction ID whose output you are basically spending, and you have to have a corresponding unlock script. There are a few other things that I'm sure you know, but I'm not going through the details. Okay, and the output structure is what, where you actually create the value that the money that you're transferring, and basically the lock script that basically says that who can spend this money. We just saw a transaction previously where you have only one input, and in the input we saw transaction ID and the unlock script, and the transaction ID was actually referring to the T offer transaction, where output is there, and that output basically is trying to spend. Okay, so now this is important. There are a few other things. End lock time. I just want to quickly say that when you make a transaction, this transaction will be picked up by the miners to validate it and approve it and so on. But you can basically delay the execution of the validation of this transaction by putting by using this end lock time field. Okay, so and basically this means you can think right now that I'm making a transaction right now here, but I want my transaction to be taken effect maybe after a week. Okay, it is pretty much like when I write a check, I might say that check can only be encashed after a week or so, and that Bitcoin also allows, and of course that field is important. And exactly how it is done, these details are given here. You can see when I share the slides. Okay. Okay, now transaction input structure, we of course have seen. I don't want to go through. There are a few other details like n sequence, but I don't need right now. And output structure, we saw that n value is basically the amount that you're transferring, and creating now, and of course a script of key, the log script, which will actually have condition to spend it. Okay, now the next important thing I want to discuss before we actually move to the protocol is the message for signature generation. You remember in the unlock script or script sig, the that we saw, for example, A was creating for its own T fulfill transaction. Every signature has to be created on a message, and I says that the signature is created on the transaction. Okay, the transaction that it is actually making. So but to be very particular, we see that what goes into that transaction, because that is important to understand some of these payment channel protocols. Okay, so here you see a special transaction here, a full transaction details. You see here what happens in this transaction. You have two inputs. You have one input here and one input here. So basically this transaction is basically consuming basically consuming balances of two UTXOs, okay, which were previously available. Okay, so and it has one output. So basically it has some money in two addresses available that it wants to spend together and send it to one output. That's what it was, this transaction. And as you say, one input, as you see, the first input is what, this is the hash 0, which is basically referring to the transaction where the first first address and its UTXOs are available, and this is the corresponding unlock script against the lock script which is available here. Okay, and similarly this is for the hash h1 is for another transaction, and this is the unlock script for the lock script which is available at this UTXO. Okay. Okay, so now when you make this transaction, as I said in the script sig, you have you have to provide two things: the public key and a signature. And we want to see how is this signature created. I said the signature is created on this transaction itself, the entire transaction. We just want to see how it is exactly created. Okay, so as I said, script sig field of every transaction input contains signature. For example, script sig 0, as you can see, it should have a signature and some public key. Okay, now the signature is generated on a well-defined message, and the message is derived from the transaction itself, entire transaction. Okay, let's denote the message by m suffix transaction, this transaction, and the signature is basically generated on the hash of the m transaction. Okay, that's of course every time we create a signature on any message, we have to apply hash that we know. So there are various ways by which you can actually create this m transaction out of transaction. Okay, and you have to be very particular which option you are choosing, and you have to also make it apparent for the miner to know that you have actually selected this option. So that you can do the following: once whatever option you have chosen, as per you actually create the message transaction, and then you apply get the signature, and then you have the signature, and at the end of the signature you basically give a information in terms of the least significant bit. Okay, uh, and of these options, and that way the miner who is going to pick up your transaction, they will know that because when they run the verification algorithm on the signature, as we saw in the execution of the transaction, they will have to find out actually that what is the message. They will have to also derive the same message from the transaction, and so therefore they should know which option is being used. Okay, and they get this information from this part here, and accordingly they will also derive the same message and run the verification algorithm. Okay, I'm going to talk about the sig hash all type option, and here you can see. So yeah, here is your transaction, and in the right you actually have the message that you derive from this transaction following the sig hash all type option as follows, and this is the message on which you basically create the signature. So as you can see, this field will remain as it is. You are actually creating signature for this field. Okay, so your hash remains here, n0 will remain as it is here. The script sig length 0, that is now replaced by okay, so that you don't worry, that's about the length part, but what is important here is this field is replaced by the corresponding lock script that is available at this transaction, because you see this is the unlock script, okay, corresponding to the lock script which is available at this transaction, and that lock script you actually put it here. Okay, so and you replace this by this, and the rest of it is as it is. And for the other input, the script sig is basically replaced by all zeros. Okay, and everything remains same, and you at the end you also provide the option n hash type option, and then you make a signature on this message, and that's the signature that you actually use it. Okay, so that's important. Now sig hash, when you use it, that's how it is created, but then as I said, there are other options, and one of the options that is useful for payment channel is basically sig hash none. Okay, at this point I maybe make it clear, the sig hash none is basically similar, but I keep this part of the field empty. Okay, and we will see why we do that. Okay, when we reach to that point. Okay, okay, so with that, let's move it. That's how the signature is generation. Okay, but now the point here is that the payment channels of course also require different more involved scripts. Okay, we just saw the P2PKH type log script, but payment channel actually requires innovative log scripts for the protocols to work. Okay, so this is m out of n multisig. Okay, here we see that you can transfer the money and lock the money to the following script. Okay, I'll just quickly send you here. For example, B can make a transfer and create the X bitcoins and lock the bitcoins to the following lock scripts. What is given here? You have M, you have n many public keys. Okay, and there is the number n, and then there is op check multi-signature verify command. That basically means that I mean, who can spend this money? This basically means that m is a number which is less than n, and it says that any, and these public keys, n public keys represents n users basically you can think of, or n addresses you can think of, and it says that any m users out of this n users, if they can come together, they can basically spend this money. Okay, and the unlock script is basically the following: you have to provide the signatures using the corresponding secret keys for these public keys. Okay, so and now you can see, if you put this unlock script and this lock script side by side, it's easy to basically it's easy to validate this transaction. Okay, because if you put the signatures here, then you put the unlock script first on the stack and the lock script after that, and then you see when the execution happens, first these data will go into the stack, then m will come, and then there is this public keys will come, Okay, and then check multisig verifies because of m and n. They will know that you have to find the m, you have to choose exactly those m public keys which are corresponding to the signatures, and basically run the signature verification algorithm on each of them, and if it is okay, then basically transaction is validated. Okay, so that's basically means that if in order to spend this money is not in the control of one user. This money is controlled by now n users in a way such that any m of them can have the power to basically spend the money. Okay, so this is like a joint control. Okay, it's like joint accounts in banks. It's like similarly it's the joint control, and they come to, I mean, they are very, very important part to play for our protocol. Okay, so as I said, this is the way it gets verified. Then there is this time locked lock scripts also, and that is the following. As I said, this is another way of making sure that even though you have now transferred the money to some user, you can ensure that that user can take action on the money up to a certain time. But if it hasn't taken control of that money, then after that time you can get the money back. Okay, so that's the whole idea. So it's also very useful, and as you can see here, I have given you the script here. Again, for example, somebody is transferring money and creating money, for example x bitcoins here, and locking the money to this lock script. Okay, and it says the following. As you can see that you see, if you do this, then that basically means that the user will not be, I mean, this is locked to the user pka, but the user will not be able to spend this money until certain time. Okay, and that's time window is here. I mean, there is various way you can actually implement this time window. I'm not going into that, but the important thing is that this is a time window which actually which is created in the future since the transaction is approved, and then this basically means that okay, the user A can basically spend this money, but not before uh, I mean before this time window is over. So if this time window is for a week, then I have transferred the money. The money is actually with the, I mean, it's controlled by the A, but only after a time. Just imagine, like if you're leaving some money with for somebody, you can say that okay, this person has to be of certain age, and then only after that the person can actually spend the money. Okay, and that you can basically enforce using this lock script. Okay, so that's also important for our protocol. Then of course we have if and else kind of a small loop, if and else kind of a small conditional structure also available as part of the lock script, and this is here. As you can see, I can make a transaction where I can actually transfer the money and lock the money to basically a lock script where, as you can see, I have a certain condition when the if statement is true and certain condition when the else statement is true. Okay, and we will see how to basically ensure that when is the if condition is true and when the else condition is true. Okay, we will see that as well. Then we have also hash locked. These are also very interesting and very new kind of transaction with the lock time and so on, and they have a lot of nice application. Here you can see the hash lock transaction is the following. I can transfer the money and lock it to the simple lock scripts. What is that? The lock script is the following. I have a op hash of some number, say, okay, I have a op hash command, and I have some data, and I have this command op equal verify, and I have this money which is locked to this lock script, and I'm basically saying that anybody who can provide me the pre-image of this data under this map will be able to get this money. Okay, so as here, as you can see, if hash 160k is equal to h, that means k is the pre-image of h, then anybody can spend this money if they provides as part of the unlock script the data K. Because if you put K here in the stack, I mean, if you now unlock script and lock script put side by side and execute, basically K go first in the stack. Then because of the op hash command, you actually compute op hash of K, and then on top of it you put H, and basically you see both of them are equal or not by using this command. If they're equal, basically you have provided the pre-image. Okay, so that shows so we saw a couple of scripts. We started with P2P, which is the most normal and most popular, but the other ones, as I said, hash lock, time locked, if and else, and of course the multisig, they are very important, and they are actually getting used for this state of art layer 2 protocols. Okay, now come to the scalability issue. I'm sorry I'm coming late, but these are the things which I have to. Okay, let's see, I still have a bit of time, then we should be able to at least introduce the protocol. Okay, so quickly let's go through the scalability. As I said, although blockchain applications have achieved quite a bit of growth, their ability to scale and increase transaction capacity is fundamentally at odds with their approach to securing through wide replication. As I said, every transaction has to go to every node in the system, and that's actually adds to the delay. Okay, so because each transaction is processed via the network has to be stored on the blockchain, there is a fundamental limit on how many transactions can be processed per second. For instance, in Bitcoin, with its 1 MB block size and a block creation rate of approximately 10 minutes, the network is currently limited to process up to only 7 transactions per second. Okay, in contrast, if you look at the other payment networks such as Visa, they actually in the peak times they basically process more than 50,000 transactions per second. Look at the wide drift here, 7 versus 50,000. And if you really want to catch up anywhere close to this number, you have to have very, very interesting protocols, and they are happening actually. So a natural solution that offers to increase the block size or block creation rate will run into problems. I mean, one way, if you want to increase, maybe you increase the block size, therefore actually you actually put in a lot of more transaction into the block for approval, or you, as you know, the block creation rate you can decrease significantly, and significant from 10 minutes, and both of them actually run into huge problems. Okay, as far as the stability of the blockchain ledger is concerned. Okay, but so, and this problem is a big problem, and it's more amplified if in the case of micro transaction, where you have low value transaction and there's no point actually. I mean, any payment network will bound to have low value transaction, and if they all have to always go to the blockchain, then of course you cannot compete with the fee and so on. And of course, on top of it, many of these low value transaction requires kind of immediate approval because they're low value. And if you see that they also take about 1 hour to confirm, and so that's not going to play out very well. Okay, so this limitation, how do you basically work around? And there is this payment channel. Okay, it's it's one of the most interesting layer 2 protocols for Bitcoin. Okay, so the primary idea is that the payment channel basically allows two users to rapidly exchange money between each other without sending transaction to the blockchain. Okay, but the point is that if you exchange money, and that too the money is Bitcoin, and that too you don't send the transaction to blockchain, how do you guarantee the security? Well, this is achieved by keeping the massive bulk of transaction off chain, of course, but using the blockchain only when parties involved in the payment channel disagrees. Okay, or when they want to close the channel. Okay, so you see that you create a off channel, basically off blockchain channel, and where you actually exchange money, and then you do the final settlement on the blockchain. Okay, and we will see that the the off-chain transactions and the final settlement, they are binded in a way such that disagreements and dishonest behaviors are basically avoided. Okay, so that's a good thing, because if you can do bulk of transaction offline and you just have one or two settlement transaction to basically summarize all the transaction, then that's basically saves a lot of your money, save a lot of your time and so on. Okay, and more importantly, that all those offline transactions, their data is not put into the blockchain, so that will reduce the load on the blockchain database also. So overall, this is a very, very interesting part, and it can, if it is done properly, it actually adds value to the blockchain based currencies, definitely. Okay, so I'm going to discuss quickly. We have worked on this area, and we have quite a few results now. But yeah, but though those are a bit advanced, but that's why I picked up a very state-of-art payment channel protocol called L2. Okay, and I just want to give you through L2 a payment channel protocol, and that will give you some idea that how this payment channel protocol works. Okay, so it's a state-of-art payment channel protocol, and this now I'm going to describe this protocol, and we see how a channel is created between two users who maybe on a day they do say maybe lots of Bitcoin transaction, but they don't want to send all of this transaction to the blockchain. So basically they create a payment channel which is off blockchain, and they do the transactions there, and then with one or two transactions they will basically summarize, and those two transactions are basically going to be on the blockchain. Okay, so these payment channels will of course they have three phases. There is this one setup phase where you create the channel, then there is this negotiation phase where you basically do a lot of off-chain transactions, and then finally you have a settlement phase where you basically close the channel and summarize your final balance. Okay, so the setup phase involves moving some funds into an address which is controlled by both the participants A and B. Okay, and then they are going to adjust this fund through multiple transaction, but they are all going to be offline. Okay, that's important. And as you can see, controlling by two participants is possible because now we have seen the multi-sig transaction and so on. Okay, now the negotiation phase is where basically they redistribute this fund which they created as part of the setup phase, and in the negotiation phase they actually do this multiple times, and okay, but this is done through offline transactions. Okay, and finally you settle basically all the transactions and basically final balance, and you close the channel. Okay, so I'm going to give you the online versions where that will prepare you for the final version of L2. Okay, which is the offline, and it actually saves a lot of lot of your time and a lot of your money by not going to online the blockchain. Okay, so let's see. So L2 online version, which is very simple. Okay, so you have both A and B, and we will see how the payment channels are created. Okay, so for that we will see that A and B will have two types of key pairs. Okay, so we call them one as settlement key pair. So basically A will have PK suffix AS, and it has its corresponding secret key SKAS. B will have its public key PKBS and its corresponding secret key SKBS, which is available with B. Okay, that's, we call it settlement key pair. We will see what their uses. There is also an update key pair, which we denote it as follows: PK suffix AU. That basically means this is the public key of AU A, and this is an update key pair. And similarly, B will also have its update key pair. The secret key is lying with P. Okay, but they will exchange these keys. So basically, A will know the key pairs of B, and B will know both the key pairs of A, as far like both the key pairs in the sense settlement and update public key. Okay. Now let's see the setup phase. So I give you the as you can see, as part of the setup phase, what happens is the following. I have a particular reason why I put this green and why this this as not green. I'll tell you. So look at this transaction TU0. TU0 is basically a transaction that A creates, for example. Okay, and this, I mean, in fact, both the transaction TU0 and TS0 is created by A. Okay, and what are those transactions? You see, we call the first transaction as the funding transaction. Okay, as part of the setup phase, where A actually transfer some money and and to this basically, it create as part of this transaction, it creates a UTXO and it put X bitcoins here, and the lock script is the following. Okay, the lock script is the following. Lock script says that that basically this there are if and else. In the if, there is a one way to spend this money, and in the else there is another way to spend this money. Okay, in the if, you see that the if branch cannot be executed until certain time window. Okay, so this OPCSV is called check sequence verify, and you see 10 OPCSV basically let the user A create a time window, and in that time window, during that time window, if any transaction is proposed, says this time window is for next 2 weeks, okay, or 1 day maybe. So then during this time period, if somebody wants to spend this money, then this that transaction will have unlock script, but that unlock script cannot be the solution to this lock script. Okay, that's the whole idea. This lock script cannot be used basically for this time window. Okay, and but during that time window, say it is 1 day, you can always use this to spend this money. Okay, that's the okay. So for 1 day, maybe after you present this transaction, for 1 day you can use this lock script and find its corresponding lock script to spend this money. But after 1 day, you can use this one. Okay, now see what is happening. It says that okay, so what are this lock script here? Let's see. Here you see that for 1 day, for certain time period here, this lock script basically specify that this money is controlled by both the user A and B using their update keys. As you can see, this is a multi-sig 2 out of 2 multi-sig lock script. Okay, so both the secret keys are required to spend this money. And which are the keys? These are update keys. But here in this, what happens? Here also the money is controlled by both of them, 2 out of 2 multi-sig, but the secret keys are required as the settlement keys. We will see that. Okay, that's how it is. Okay, now A creates this transaction, but A immediately will not make this transaction to the Bitcoin network. Okay, A will simply have this transaction. Okay, and A will now, because A is actually creating this money, there is no way B is coming into picture here, but still A is giving the control of this money to B also. You see, once it is created and B doesn't cooperate, because in both the cases the money is now controlled by both A and B. If B doesn't cooperate, then this money is lost forever. Okay, so before it actually makes this transaction to the network, A will say contact B and say, okay, I will going to make this transaction, but before I do that, you give me the signature, you give me your signature using your SK, secret key SK, corresponding to the settlement key. Okay, so you give me your signature on a transaction that I'm making here and using your secret key. Okay, so basically I'm writing a check where you give me your signature, and the check mentions that the money is now controlled, X Bitcoin money that can be spent, and it is controlled by the user A. Okay, so basically it says, okay, I'm going to create a channel. In the channel, the money will be controlled by both of us, but that will be controlled up to certain time. Okay, and during that time, if we don't act on that money, then after that time I should be getting my money back. Okay, and I mean I should be getting my money back, and that guarantee, that means I'm actually have that check written already. You should sign it. So B have no problem signing it, because B is not anyway spending its own money at this point. Okay, it's just that money is created by A, and the money will be there up to certain time in which both of them can actually control it. And after that time, if we don't do anything with the money should go back to A. But because it is also specified that this money is controlled by both of them during after that point also, so therefore B should give its signature ahead of time. Okay, once B gives this, what happens now? A will go ahead and broadcast this transaction, and that basically means the transaction, the money is created now, but this transaction is not broadcasted. A basically keeps the transaction with itself. Okay, now at this point there is a money there, it is controlled by both A and B. Okay, uh, okay, that's what it is. Okay, and if anything to be done, this has to be done before certain time window, and in that these public keys are used by both A and B. Okay, so let's look at once you have this, for example, PU0 and S0, that was I was putting here. But now you suddenly decided that, okay, out of this X Bitcoins, which is already available, now A wants to send this, out of X 1 Bitcoin to B. Okay, so that basically means that out of this available fund, 1 Bitcoin should go to B, and rest of should still remain under the control of both. Okay, and for that to happen, you see, for that to happen now, and we can actually make both of them can agree, and basically because if it is less than this time window, both of them actually can spend it and basically get this done. Okay, but the way you do it is as follows: you actually spend this money, and basically you create another transaction, both of them, and there now you basically put the money again here, but now because you spend this money, and basically you create this money, and you again put them in both of the control as per this fashion. Okay, and you create another settlement transaction which basically specifies now that 1 Bitcoin will be under the control of B. Yeah, this is slight typo here. This should be A and this should be B. Okay, so 1 Bitcoin will go to B, and basically the rest of the X minus 1 Bitcoins after that time window will remain with A. Okay, so on the blockchain you still see that the X Bitcoins is basically controlled by both of them, but we know that there is a transaction which is available with both of them, which if broadcasted, then basically this money will be redistributed in the fashion. Now if you want to continue further, then of course, say you want to make another transfer and 1 Bitcoin to the user B, and then X minus 2 Bitcoins will remain in the control of A after a certain time. Then what happens? You again make another transaction, basically and where you still show that the X Bitcoins is basically, as far as view is concerned of everyone, the X Bitcoins is controlled by both of them. But we know that now there is a transaction which is available, which is basically distributing the fund in the following fashion. And at this point, if they want to terminate their, engagement, then basically they can simply, make this transaction broadcast to the network, and that way, basically the channel is closed, and the X Bitcoins are basically now, out of the X, 2 will go to the B, and X minus 2 will go to the A. Basically, that's how X minus 2 will remain with the A. Okay. But I mean, these details, you actually need fewer more details to perfectly grasp this. But yeah, because of the time constraint, yeah, maybe it's not possible here. But the idea here is that, okay, that you basically create a fund and you redistribute the fund, okay, and that redistribution is not available with the, with it's not available for everybody to see. It's between only A and B. That's the whole point here. But now, if you go to the offline phase, you actually, do it nicely, where you actually don't make this transaction. In fact, the green transaction, as you see, you actually do a lot of these updates, but you only at the end make one transaction and basically, agree on the final redistribution. Okay. I think I am already past 1:15, so I will have to stop, but I will share these slides, and if you want, you can basically, these have all the details, so you can basically go through if any of you are interested, and go through the offline phase as well. Okay, maybe I'll stop here. Okay, if there is any question, I can take up. If any question, I can take up.
Dear participants, if you have any queries, you can post in the chat window, or you can ask, sir. Mahavir sir, thank you so much for sharing your knowledge. I think participants won't have any doubt. If they have doubt, we'll be sharing your email ID, sir. If they have any queries, they will contact you, sir.
No, sure, definitely,
Yeah.
definitely. Okay.
Thank you for your wonderful speech, sir, regarding the blockchain openings with respect to research problems, ideas. Thank you so much, sir.
Thank you, everyone. Thank you.
Thank you, sir.